we begin. Briefly back to DC motor and back to speed control. Speed control of DC motor. I'll do shunt. Check what happened in series. Briefly, just where we began last time, we said from motor equation, we say is what? We say V is equal to what? EB plus IARA. India. Then we said make EB the subject. Then you say EB is equal to V minus IARA. India. And EB is the same as the flux, the Z, which is the what? Number of conductors, the speed N, and P, what is number of poles and pole pairs, A, the pole pairs. And now, this is equal to V minus IA RA. India. So, because our interest is N, which is the what? The speed. So, we are saying speed N is equal to what? V IA RA over Z P over what? P over A. Cynthia. And I told you last week, the number of poles you can manipulate. It was done by the designer. Pole pairs by the designer. Number of conductors by designer. So holding ZPA constant, then it means N is directly proportional to V IA RA over what? Flux. And therefore, for us to get the factor that influences the speed of the motor, we said there must be the applied voltage, the armature drop, the IARA, the armature drop, and finally the flux. The flux directly linked to the field. And therefore, we have how many methods of speed control? We have 3 methods of speed control. We said number 1 is what we call the field control, which is also called variation of the flux. And then we have number 2, armature control, which is also called rheostatic. And then finally you have the voltage control, and I told you there are about 2 methods of voltage control if you check, but the major one we look here is what? Ward Leonard. Coming from here, because I want, as we discuss each of them, then we do the example plus other things, we need to know what is the speed equation. The speed equation. The DC speed equation, let N1 be the initial speed. So we have realized N1, therefore we can say is equal to what? I'm back here. Cynthia, let me handle from here. Yeah? So V do not change. The voltage is the same from the source, right? So it will be V minus IA may change. Cynthia, RA will not change. Over the flux 1, sindio? And N2 be the final what? Final speed. So N2 will be what? V minus IA2, sindio? RA over flux what? Flux 2. Actually, what is V minus IARA? Is EB. Kweli? Sindio? Therefore, we can reduce this to say this is EB1 over flux what? Ni kweli? And this one you can reduce, in the case of 2, EB2 flux what? 2. Sindio? Compare, let's assume this is equation 1, this is equation 2. Compare equation 2 to 1. Compare means 1 is sitting over. So that means we are comparing to N2 over N1. So that would mean this is EB what? EB2 over, I just want to be barbaric without mathematical sense, right? Yeah. Times nini? See, tunaleta hii. This one is equal to this one, sindio? So we are saying it is EB1, it is flux 1, upside down, sindio? Over EB1, sindio? Yeah? Somebody stuck, huh? You take this one, you are dividing upside down, huh? So finally we can reduce that E2 N2 N1 is equal to EB2 over EB what? 1 times flux 1 over flux 2. And current also. Current can be current 1 over current 2. So this is called the speed what? The speed equation. It's called the speed equation. Very important because we'll be using that equation. That's why I wanted us to derive the equation before I come to discussion of each method, Ashanta. And therefore, we can get to what we call the field control. Number 1, field control. What happened in field control? Field control, we are saying that introduce the variable resistor in series with the what? With the field. If you are talking about a field, then we are saying introduce a variable resistor in series with the what? With the field. So when we do that, field is here. So I can introduce a variable resistor this is a variable resistor, the rheostat, and this is the field. This is the armature. The current is getting through the armature and the field, and the final current coming, and the voltage. So once we introduce, this is the field, we introduce a variable resistor in series with the field, then by varying this field, you are varying the field current, right? And therefore, this will affect the speed according to the equation we receive here. So you can say, as seen, N is inversely proportional to the flux. As seen, N is inversely proportional to the what? to the flux. Andika hiyo kwanza. The inverse proportional to the flux, and therefore by varying the flux, speed varies. By varying the flux, the speed varies. By varying the flux, speed varies. This can be achieved by inserting a variable resistor. This can be achieved by inserting a variable resistor in series with the field. This can be achieved by inserting a variable resistor in series with the field. Limitation of this method. Limitation of this method, we are saying any adverse weakening weakening of the field can lead to poor commutation. Can lead to poor what? Commutation. I don't know whether I define commutation. You need to understand what is commutation in DC. Very important. So what is that commutation? Commutation is the process of transferring the induced EMF from the armature conductors to external circuits. It's the process of transferring the induced EMF from the armature conductors. Remember, it is in the armature conductor that we cook the EMF. So they need to be transferred for use. So the process of making them effective into the external circuits is called commu. So this method must be effective for the machine to be effective, right? Example. A 500 volts shunt motor, 500 volt shunt motor, run at its normal speed of 250 RPM, normal speed of 250 RPM. When the armature current is 200 amps, when the armature current is 200 amps, full stop. The resistance of the armature is 0.12 ohms. 0.12 ohms. Calculate the speed when a resistance is inserted in the field. A resistance is inserted in the field reducing the shunt field to 80% of the normal. Reducing the shunt field to 80% of the normal. and the armature current to 100 amps. And armature current to 100 amps. So what are we given? A voltage of 500 volts, initial speed 250 RPM, armature resistance 0.12 ohms, current initial is how much? 200, Sindio? And current final 100. What else is given? What else is given in those details? There's something that the field was reduced to 80% of the initial. So I want to assume initial flux 1 was 100%. Sindio? Flux 2 is 80% of the initial. That means it is 0.8 of flux 1. Kweli? That's a good reasoning. Therefore, let's get to we need to get the back EMF initial before we inserting. Sindio? Yeah? Case 1. Case 1. Before inserting. Before inserting the resistance. So what are we saying? The EB1 is equal to, will be equal to V minus IA1 RA. Ni kweli? Yes? And therefore, we are saying this is 500 minus 200 times 0.1 what? 2. Sindio? That will give us how much? Huh? 476 volts. We also need to get EB2, which is V minus IA2 R, and this is 500 minus 100 times 0.12. This is 488. 488. And therefore, let's come to the speed equation. The speed equation says N2 over N1 is equal to EB2 EB1 times flux 1 over flux 2. So what is N2? That's what we need, because we are asked the speed. So we don't know N2, but we know N1 250. Clearly, is equal to what? EB2 488, EB1 476 times flux 1 over 0.8 flux 1. Hapo tumeelewana? So that you find N2 from there. Find N2. Yeah? 338. This is speed, RPM. 2, we said it's called the armature control, or also called rheostatic. So when you talk about armature, now shifting the variable resistor from the field to the armature circuit. So we are going to connect the variable resistor in series with the what? Armature, right? So we can say this method is used when a speed below no load is required. When a speed below no load is required. Below no load. Below no load is required. The voltage across the armature is varied by inserting a variable resistor. Called the controller resistor. In series with the armature. In series with the armature. The shunt field. So we are saying we are introducing a controller resistance in series with the armature. As you continue varying the controller resistor, you vary the armature drop, and therefore the what? The speed. Example. A 200 volts DC shunt motor, 200 volts DC shunt motor running at 1000 RPM, takes an armature current of 17.5 amps, full stop. If it is required to reduce the speed, to 600 RPM, what must be the value of the resistance? To be inserted? The value of the resistance to be inserted in the armature circuit. If the original armature resistance is 0.4, original armature resistance is 0.4 ohms. 0.4 ohms. In bracket says, take the armature current to be constant during the process. So what do you have? We have V of 200 volts, RA 0.4, I 17.5. What else? N1 1000, N2 600, 1000 RPM. RPM. Nivo. What else? What else have we forgotten? Now, again, we need to take, in case 1, when the speed is 1000, when the speed is 1000. So we are saying EB1 is equal to V minus IA1 RA. Sindio? So we are saying, this is 200 minus, what is IA? 17.5 times 0.4. Sindio? That should give you the back EMF. Huh? EB2 is equal to this IA into RA plus R, where we are saying let R be the resistance inserted in the armature. What? Let R be the resistance inserted in the armature circuits. Are you getting that fact? So now the resistance in series is the small r, right? Yeah. To change the speed. So we can just write that equation by saying EB2, we don't know, is equal to 200 minus 17.5 into 0.4 plus what? R. Leave that equation there. That's the equation we need so that we can get, because we have two unknown, right? And since the current was constant, we can say N2 over N1 is equal to EB2 over EB what? 1. Current is constant. So we EB2 600, EB1 1000 is equal to EB2 that we don't know. EB1 is 193. So what is EB2? What is EB2? Hmm? 115.8. So take it back here, back to our equation. Then we can say 115.8 is equal to 200 minus 17.5 into 0.4 plus R. So work get the value of R. Whether you're using board mass or what, you know. DC motor braking. Braking methods. So broadly, these are categorized into, we call electric braking, let me start with the mechanical braking for the reason, and 2, electric what? Braking. Electric braking, mechanical braking was not so smooth. Because when you brake mechanically, you need to skid. So the mechanical braking depends on the surface on which you are braking, and this is why we are not using mechanical. And therefore, the electrical braking has been common, and the main types of braking under electric braking, we have what we call dynamic braking, also called rheostatic braking. Then we have what we call the plugging. Plugging is also called reversal of current braking. And finally, in this category, we have what we call regenerative. Regenerative braking. So actually we have those classes of braking that we need to discuss. So we are starting with dynamic. Dynamic, we can say, in this method, disconnect the armature from the supply. Disconnect the armature from the supply and connect it across. Connect it across a variable resistor. Connect it across the variable resistor. Due to this, the motor will start to act as a generator. The motor starts to act as a generator. So we are doing dynamic. So what are we saying? While so when you disconnect it from the supply and connect it across a variable resistor, it begins to do what? This will still rotating, but now it's not getting the power, so it becomes a generator, right? And therefore, the final force opposes the initial, and then it will come to what? To brake. So that's what we call dynamic. It will continue braking, but now generating, right? And then that force will try to oppose the initial and then come to halt. So we need to get the equation for this. We want to get the current moving here, the armature current. So the armature current, this is the equation. The armature current IA is given by, remember, this current is now only, V is here, but here there is what? The back EMF developed. So it's only the back EMF that is operating here, because the voltage applied is not connected, right? So we are saying I is equal to EB over R plus the other R. There's two R, sorry. This is the armature one. Please ensure it is armature. Yeah? It's the armature plus the one that makes to break. So, but we know EB is equal to flux Z and P over what? Right? Therefore, I is equal to flux Z and P over A over RA plus the braking resistance. So, but the braking torque, T braking, is given by 1 over 2 pi I flux Z P over A. The braking torque is given by 1 over 2 pi the current, the flux Z over P over A. Now we need to replace this I, because you know I is equal to this one, isn't it? So that means TB is equal to 1 over 2 pi, let me bring flux here, Z P over A, introduce this, that is the flux Z and P over A over R plus the resistance, right? Try to cross here, open this bracket. What will you have? 1 over 2 flux is squared, clearly. Z is squared, right? P over A, but there's a N, right? This is equal to TB, but over RAR. Taking all this as constant, the other values as constant, then we can say TB is equal to flux flux squared N. So introduce a K as the constant, K1 being 1 over 2 pi ZPA squared RA. Let me write it down. All the others as constant, right? Which is K. Then TB will be that K, the constant. I want to introduce that K here. K1 is equal to 1 over 2 pi ZP over A squared, right? Over RAR. Therefore, TB is equal to K1 flux squared N. Because the same question will come, explain the dynamic and hence give the equation. Yeah? There are very few steps here. You only remember you need to get the current. You get the current, you remember the torque equation. Remember the torque equation, you substitute the value of the current and you are here. There are only 3 steps. Then we have what we called the plugging. Number 2, plugging or reversal of current. Plugging or reversal of current. So you can say in this method, the armature current is disconnected. I mean, the armature circuit is disconnected from the supply and connected across, not connected, and reversed, and reversed, such that the motor begin to run in opposite direction, so that the motor start to run in opposite direction. The shunt field, and this is the braking resistor R and armature resistor. So when we overturn the connections and then put a braking resistance, then the motor will brake. Again, here we need to get to the equation. The EB induced, point to note, due to this, the applied voltage and back EMF operates in the same direction. Due to this, the applied voltage and the back EMF will try to operate in the same what? Direction. And therefore, when we come here, we say the armature current IA is equal to V plus EB over RA plus R. Right? Yeah? Because they are operating in the same direction, so we add the two, right? But we know that this can be written as EB over. Tumekosa? And EB is equal to the flux Z N P over A over RA R. Because that was the LCM, right? But the braking torque, TB, we have realized is 1 over 2 pi the flux Z P over A times the armature what? The armature current. The braking torque is this equation times the armature current, where the armature current is this one. Right? So we substitute the armature current. TB is equal to what? We substitute the armature current. We start with 2 pi flux Z. So we have V over RAR plus flux Z N P over A over RAR. It's okay? So break that bracket. What will you have? Break that bracket as long as it is. So we now have 1 over 2 pi flux P over A V, sindio? Over R over A plus pande hiyo 1 over 2 pi flux squared. Z squared P over A. Let me hold it like this. Squared under N over R. Right? So let K1 represent 1 over 2 pi Z P over N over RAR, and K2 1 over 2 pi Z P over A squared over R. So what will we have? TB is equal to what? K1 flux N. Kweli? V. V. Right? Plus K2 flux squared N. Kweli? So this is the equation. That's the equation. Next is regenerative. So in generative we are saying in this method is used when an overhauling used when an overhaul characteristic of the load is present when there's overhauling characteristics of the motor. That means the back EMF is greater than the applied voltage. Remember, this is a motor, and if you recall from the motor equation, we said V is equal to EB plus IARA, right? Yeah? But in this case, EB is greater than what? Due to the load. So that means this thing becomes a what? Yeah? If EB, I don't know how to put it greater. Greater is this one?
No, that is
EV.
Yeah.
Greater than V, then this case can only be in a generator. Right? So this will be a generator. So once we cause the load to be more, the load to cause the EB to be more than the back EMF, then instead of motoring, this will be generating, and therefore it will stop. So actually, the circuit is just like a normal generator circuit. But this one is going up. So once it's going up, it's now a generator, not a motor. And therefore, we will have what we call the regenerative braking. So that's all about speed and motor braking. I'll just introduce what you call tests. We'll pick from there. So why do you do tests? Why would you do a test? Yeah? Why would you do a test in a machine? To ascertain the effectiveness, the efficiency of the machine. So that introduces you that if efficiency is what we need, then efficiency is given by the power out over power what? True. It's power out over power in. But power out can also be written as power in minus losses. True. Power out is equal to in minus losses. So you realize that in a motor, in the case of a motor, we know the power that we are getting from the source, right? But we don't know the output power. So efficiency in a motor will be expressed by P in minus loss over P in times 100. But when you're talking about generator efficiency will be given by P out over P out plus loss. As in generator we know the power you are taking out. We don't know what is in the engine. So for you to get what is in the engine, it means is the P out plus loss. To get P what? P in. So we'll be interchanging these equations as we go to the test. Now, of course, that's an expression. Can either be a ratio or a percentage. These are communication. That's English now. So we basically have I've realized there's about 7 tests, but I will concentrate on about 3. There are about 7 tests. Yeah? But we'll consider about 3 tests that we do here. So we will do what we call the braking test. And then we have what we call Swinburne. These are methods. Swinburne tests. And then 3 Hopkinson tests. So that's where we pick from. The Swinburne test. So in the Swinburne test, the thing we need to know is that the motor is run at no load. We run the motor on no load. And with the losses known, the efficiency can be determined at any desired load. That we run the machine on no load. The only power needed here is the no load. Right? Now once the losses are known, then we can run the machine on full load. Why we run the machine on no load, this case, is to know main reason here is to determine the stray losses. They are also called constant losses. This is the main aim. We need to get the constant losses. So we start by, in that case 1, no load. So assume to gonna So this is the circuit at no load. We run the machine at no load. Case 1, no load. Sorry, no load. So what do we need? We need to know the field current that is passing here. We need to get the no load power. The no load input will be given by the voltage times the no load current. Ni kweli? Huh? That is the input getting to the system, right? So once we get the that, we also need to get the no load armature current. We want to write it like A naught E. The current to a point is equal to current leaving a point. So the current going through here is no load, right? And the no load one, the armature no load is getting here in the shunt. So that means the no load armature current will be the supply minus the shunt. True? Yeah? Is there? The current here is equal to the current coming minus the shunt current, right? And therefore, shunt current we can know because this and this are in parallel against a supply voltage V, right? And therefore, I shunt is equal to V over R what? R shunt. Yeah? Because this voltage and this voltage is the same as the source voltage because they are in parallel. So we can get the I shunt. So this is the armature no load current. And therefore we can get what we call the armature copper loss. Right? The armature copper loss, will be given by IA naught squared RA. Right? Yeah? IA or the naught times the armature resistance. And once we get that, therefore, the constant loss the stray loss is equal to, that is VWC is equal to the input minus the loss. So we are saying this is equal to V I naught minus I naught squared RA. So, some people wameanza kutoka kwa gari. We are saying the loss is here, right? The stray losses is any other loss that not within the armature. There are losses due to the brushes. There are losses due to the field. So we are saying the other losses, having the armature loss, we subtract from the input that was given to this motor. Therefore, the remaining is the stray what? Stray losses, right? And therefore, that's why we're saying it is input minus losses. So WC is equal to this one. This is why we run the motor on what? On no load. Once we get the stray losses, then we can get to case 2 full load. Full load, where we are now saying the motor is now run on full load. The full load current IA, the shunt R, and the full load current L, and the voltage coming from the source. Again, the full load full load input will be given by V times the input current, right? At input, the voltage times this give us the input to this system when we now run it at full load. And again, we need to get the full load armature current. Armature current IA, which is equal to I full load minus what? Shunt. The full load one. We have only changed the values. Procedure is the same. Then we get the armature copper loss, which will be IA RA, right? So once we get this, we can now get the total loss for the motor. So the total loss will be given by, I want to arrange them. One is the armature copper loss at this point, which is IA. This is a, and then WC. That we call it constant loss, which is W what? C. So the total loss is equal to IA squared RA times W what? C. So from here we can get the efficiency of the motor because you have the total losses, right? Yeah? We can get the total efficiency. So we say efficiency as a motor. Hapa ni motor kwanza. So in a motor, efficiency we realize is equal to P in minus loss over P in. So what is the P in? P in is V IL, right? Minus losses, which include what? IA squared RA plus W what? C all over W, all over the input L times 100. This guy was very careful about 100. Times 100. That is as a what? As a motor. Which paper? There's a paper you gave back to me. There's a question with. Let me use the last point so that I don't miss. And then that is A. B, efficiency as a what? As a generator. In generator, the WC do not change. Yeah? This one you hold constant. It will never change, but we change here. So in a generator, I is equal to I load plus I what? Equally? Huh? Yeah. Right? And therefore we can say the armature copper loss is equal to IA RA. Right? Therefore total loss is equal to IA RA plus W what? C. What is the efficiency in a generator? Is P out over P out plus what? Losses. So again, you realize that things change. In a generator, this thing is now going up. Sindio? And therefore, this one will go this way. True. Therefore, the output, not the output, generator output, output will be VIL. Manielewa? Because in a generator, it is this engine that produces power, right? And then it gets to fill for excitation, and this is now the output current. So the output power is V times IL. So we come here, we say V out is VIL over VIL plus IA squared RA plus W what? Times 100. And then we put this example. This was in an acre. What I have here is on an acre. Example. A Swinburne test was performed on a 230 volt. Was performed on a 230 volts DC shunt motor. 230 volt DC shunt motor, and gave the following results. You can put them in line. The following results. No load current. No load current 4 amps. No load current 4 amps. Shunt resistance 280 ohms. Armature resistance 0.8 ohms. Zero 0.6, sorry. If the armature draws a current of 50 amps from the supply, determine the full load efficiency. Determine the full load efficiency as a motor. Full load efficiency as what? As a motor. Full load efficiency as a motor. So we have all the data. V is equal to 230. So what do? We must run the motor case 1. Solution. Case 1, no load. What is the no load current? 4 amps. Right? No load current, 4 amps. So we start with the no load input. No load input, which is V I naught is equal to 230 times 4. True? Yeah? 230 times 4. Now let me sketch it here. And then what will be the I shunt? I shunt is V over R shunt. Yeah? So that we get the current moving to the field. Yeah? Since they are in parallel to the supplied what? Voltage. So we are saying this is 230 divided by 280. 230 divided by 280. 0. Yeah? 82 amps. Once you get that, then you can get the no load armature current, which is I naught, which is I naught minus I shunt, right? I naught, the current here, minus the I shunt, you get this one getting down, right? So we are saying this is 4 minus 0.8, 3 point, Point 2, so this is 1.8 is the armature no load, and therefore we can get the armature copper loss given by I naught squared array. This is 3.18 squared times 0.6. Armature current was 0.6 times 0.6. What? How much? 6 point? 6.07 amps, huh? That is current to the armature. And therefore, watts, huh? Therefore, the constant loss, W what? C is equal to the input minus this copper loss. Right? So what is the input? Watu kupeana answer hapa. Times 4? 920 watts. So we are saying 920 watts minus 6.07 is the stray loss. That is a stray loss. That is 13.93 is the stray loss, W what? So once we get WC, the stray loss, that's why we run this machine in case what? Case 1. So we now go to running in case 2. Case 2, full load. What is the full load current? 50. Did you see that? Yeah? 50. So that means the input is equal to V I full load, which is 230 times 50. At full load, that will be the input. And the armature current armature current IA will be I minus I shunt, which is 50 minus 0.82. Those answers, so that we proceed. In this is how much? 11 watts, huh? This would be 40, 49, huh? 18, huh? And then we get the armature copper loss, which is IA squared array. What are we saying? 49.18 squared times 0.6 is the new copper loss at full load. New copper loss at full load. How much? 14.2 watts. Then what are the question? Determine the efficiency as a what? Efficiency as a motor. So efficiency as a motor means what is the total loss? No, motor input. Motor input that we have is V times IL, which is 500 watts. Losses, we have the armature copper loss, IA squared RA, which is constant loss, what is the constant loss? WC 913.3 watts. Total losses, add the two. 23.13 watts. Therefore, efficiency as a motor is P in minus loss over P in times 100. Our P in is 11,500 minus, we have the figure, minus 2365.13 over 11,500 times 100 will give you the efficiency. What you can do, also determine the efficiency as a what? It's a generator. We said there's a change. The change here will be plus. Right? Yeah. Here will be plus. That's a generator. So our next will be Hopkinson tests. I will do what you call Hopkinson test.